Okay, last time we talked about asymmetric public key cryptography. Let's review that. Why do we need public key cryptography? So it's initially proposed to do encryption and decryption, and later on we realized that it's not just encryption, decryption. It can do many more things. Number one, key distribution. So when we talk about key distribution, we actually mean that when we use private key crypto system, we need to have a secure channel. So this secure channel cannot be established using private key crypto systems. So that is why the standalone private key crypto system is not complete. So actually, with the help of public key cryptography, we can really fill out this blank, okay, this gap between the establish this gap of establishing a secure channel. So this can be achieved by using public key cryptography. That's really important. So that's number one. Number two, digital signature as well. And actually, this is related to building up a secure channel as well. So even though you can use public key cryptography to build up to establish a secure channel, we still cannot verify the authenticity of any party. So this has to be done using digital signature as well. So in a complete system, we need to have three things: key distribution, digital signatures, which can both be achieved using public key cryptography, and then the secure channel could be built. In that case, we can use private key cryptography. This actually makes e-commerce or online shopping possible. Let's take a look at some differences, key differences between public key and private key cryptographies. So the private key cryptography, two parties must trust each other. Okay? And the public key cryptography, the two parties do not need to trust each other. So number one is you have to have a secure channel, and then you trust each other. Because of the existence of a secure channel, you can trust it. You trust that, then you can keep going. For public key, you don't need to trust each other. Okay. So private key cryptography both share the same key. Okay. For public key cryptography, you don't have to share the same key. And then private key cryptography is typically faster, and it's a lot faster. It's not just a little bit faster; it's a lot, by huge margin. For example, let's take. Let me give you guys an idea. A few years ago, I think like 7-8 years ago, I was leading a undergraduate project. I was supervising some undergraduate to implement public key crypto system. We're using elliptic curves, and the students they wrote a project using software. They actually wrote an app on Android system. So for AES, for both AES and elliptic curve, that's already the fastest. So for elliptic curves, one encryption takes about almost like 1 second. Okay. For RSA, at that moment, I was using HTC, an old version. They actually implemented RSA as well. It takes almost like 10 seconds to do one encryption. And for AES, it's like less than 100 milliseconds. It's pretty fast. Less than 100, like 50, 60 milliseconds. And then elliptic curve crypto system, which is asymmetric, took about 1 second. So it's almost, like 50, 60 times faster. So that's a huge difference. So So it's faster. Public key is slow, private key is faster. There's some examples like this. And then we already covered the DES, okay? We won't cover these two, okay, because they're, we only cover DES and AES for block ciphers. These are block ciphers as well, because we really don't need to cover this much, because they are pretty similar. And for public key crypto systems, we will cover RSA. We'll actually cover it today. And alpha-mall, identity curve, and many others as well. They're different. Okay. And digital signature. Digital signature is a functional equivalence of handwritten signature. Okay, so a handwritten signature, I should say it's not just a signature, because a signature is is not bound to some data. I should say your ID card. So your ID card has some information: your name, your date of birth. Okay, your many others as well, right? For example, like whether you have military service, that kind of thing. That's your ID card. Okay. So in Taiwan, we have an ID card. In the US, we have social security number, something like that. Because there's no ID card. I mean, you can have state ID in the US, but normally, if you have a driver's license, you really don't need a state ID. Okay. Now in Taiwan, this ID card becomes redundant as well, because everybody has a 健保卡. So your ID card is really not necessary. Right? Or maybe the driver's license is not necessary either. Anyway, so the ID card, that's your basic information. And then, so the signature is something like that. You can show your signature, but it's bound to some data. Normally you have a document, and then you attach a signature with it. And that signature is an output of the document. So your document and your key are both regarded as the input of a digital signature. So it has these properties. So first, it's easy for legitimate users to sign. So if you want to sign a document, that means you acknowledge the content of this document, and you possess your private key to sign. Okay? So it's easy for legitimate users to sign, but hard for anyone to forge. Okay? And it's also easy for anybody to verify. And it depends on the message. Okay, so it's bound to a message. And in many cases, it's a reverse use of some public key crypto system. So it's a kind of like inverting a function. So the signing operation depends on the private key, and then the verification depends on a public key. So it's almost the opposite. So for encryption, asymmetric encryption, the encryption operation depends on the public key, right? And the digital signature is the reverse. The sign depends on the private key, and then the verify depends on the public key. So in many cases, it's the opposite use of a crypto system. Sometimes you have standalone digital signatures as well. For example, like DSA, we'll talk about that later. Okay. So only the signer can generate a valid signature, because only the signer has a private key. Okay. And then everybody can verify. Okay. For encryption, everybody can encrypt using a public key, because your public key is public. Everybody has public. But for decryption, only the legitimate user can decrypt. So it's the exact opposite. So in the case of RSA, it's the exact opposite. So the decryption of RSA is exactly the same as a RSA signature for signing operation. Okay. So that's the idea. Okay. So now we're going to talk about RSA. So this is probably the most important lecture throughout this course, because I hope that RSA is the last algorithm to be forgotten. Okay, we'll be covering one-way functions, which is a building block and the vital building block of RSA, and we also need a little bit of number theory for RSA in order to facilitate the introduction. And also, we'll talk about RSA, digital signature. It's the same. Okay. Number one, a one-way trapdoor function. So what's a one-way trapdoor function? It's a one-way function with a trapdoor. We'll talk about trapdoor later. So let's first talk about one-way function. That's the most primitive, basic primitive for crypto system, the most important building block. That's a one-way function. Informally, that's a function which is easy to compute but hard to invert. There's some mathematical problems. They have this property. Okay? In one direction, it's easy. In another direction, it's hard. There's not too many of them. Actually, if you guys can come up with a one-way function, you can probably extend it to an asymmetric crypto system. So this really depends on these crypto systems really depends on one-way functions. Okay. So throughout these 50 years of development, there are only very, very limited number of one-way functions. And then the most popular ones, there are only two. One of them is called factorization, the other is discrete log. There are others as well, okay? So maybe the really significant ones are I would say less than 5, okay? The most popular ones are only two. We'll only introduce these two. Okay, the factorization problem. This is the well-known candidate. It's also the first one-way function. Let's think about this. First let's think about this way, okay? Given two prime numbers, P and Q, okay? Just one direction is you multiply them. So that's multiplication, okay? How to do that conversely? Conversely is that you're given a number and you know that it's a product of two primes, but you don't know what primes they are, okay? And the goal is to factorize n to get back P and Q. So there's two directions, right? Two directions. So one direction is you're given PQ, you're given P and Q, okay? And then the output is P times Q. The opposite direction is you're given this, you're given n, and then you factorize P and Q. This direction is very hard. How hard it is? How hard? Actually, we cannot analyze, so we don't know. But this is an extremely hard problem to really to quantize the difficulty of factorization. It's extremely difficult. So far, no mathematicians can do that to a satisfactory extent. No. But we know that it's extremely hard. so anyway, some students may not like this because mathematicians don't like this. Because mathematicians think you cannot quantize, right? That's because your math is not good enough. But for some reason, this problem is just so hard. After 40 years of development, hundreds of thousands of mathematicians, they are really smart people. They're researching on this. So far, there's still no satisfactory conclusions. No, we don't know. So the answer is we don't know how hard it is. But those scientists, those mathematicians, they really think hard, but they couldn't find a way to factorize this P and Q efficiently. Okay, so anyway, we believe that It's hard. So that's one-way function. This is one example. A one-way trapdoor function is a one-way function with a trapdoor. So what's a trapdoor? A trapdoor is a piece of kind of like a piece of secret information. With that information, it's easy to invert. Yeah. Without that piece of information, it's extremely difficult to invert. So there exists some secret information called the trapdoor. So with that piece of information, in this case, the trapdoor is P. Let's say it's P. Okay, you invert it. How to invert? If you already know P, then you just divide N by P, you get Q. So that's secret information. You get P or Q. You get either one of them, then the other is easy to compute. So that's a trapdoor. Okay. And we say it's computationally infeasible to invert F without knowing the trapdoor. Okay? It's computationally infeasible. In this case, it's computationally infeasible. But theoretically, we really can't prove it. Okay, we really can't. But this is engineering. It's not math, so it's good enough. Mathematicians are not happy, but it works. 所以这个真是这样子啊，这个。那么这边同学们就会可以感觉到理论跟实物的差距啊。这个地方其实理论还蛮粗糙的啊，相当的粗糙。因为到底因数分解有多难呢？到目前为止，我们只能说数学家还不知道有多难。因为没有一个有效的没有一个很漂亮的理论告诉你它到底有多难啊。目前是这样，经过了40几年的发展，都没有一个很有效的一个方法，让它可以去做因数分解，没有一个非常快的方法，都很慢。可是这样子并没有办法证明说这样一定很慢啊，说不定这些人你就数学很烂，所以你数学很烂，你找不到一个有效的方法啊，你跟我说这样你可以证明很慢，这个不对的，不行这样子，对不对？你做不出来，你怎么能说别人做不出来？搞不好就真的像费马最后定理一样，300年之后有人做出来了，对不对？所以说这个东西就是这样子，对啊，费马最后定理也是啊，差不多300年了。我同学知道，数学上很多的发展都是这个样子。那个所谓费马最后定理啊，我们同学可能应该听过啊，就是说 x 的 n 次方加上 y 的 n 次方等于 z 的 n 次方。这个东西如果在整数 x y z 在整数解只有000啊，除了000外没有整数解。300多年前，法国数学家费马这个费马很妙，那个费马。然后我们就会提到费马，因为我们等一下讲 number theory 就会讲到费马。那费马很妙，他这个是一个数学家 Pierre Fermat。这数学家最妙就是说，第一个他是个业余的数学家，他是业余的，就是说呢，我们可以说这费马是最后一个业余的数学家，那本身是贵族，所以这个费马呢，我们知道贵族每天就是吃喝，就是他不用为他的这个吃喝烦恼。那一般的其他的我们平常的平民老百姓都要努力工作，费马不用啊。那么一般大部分贵族都喜欢打猎嘛，为什么喜欢打猎？就是有个活动，不然每天闲在家里，你家里又没有电视，对不对？那个时代是没有电视的，所以都不知道干嘛的。那他们活动就打猎，那时候费马是这样。那像那个以前法王路易16，法国国王路易16就是被砍头的那个他就是写日记，他每天打猎，然后他日记上面就写说今天打了多少头，今天的猎物是2只羊这是他的日记，就是这样子，对啊，这是法王路易16。其实我们知道法王路易16其实朋友们如果去看他这个就是相关的这个史料，在法国大革命当天法国大革命已经攻入巴士底监狱了，他要写日记，你知道当天日记写什么吗？写了2个字：无事，没有事情发生。因为当天没有去打猎，也没打猎，无事。实际上已经报名已经攻进了巴士底监狱，这是贵族讲。 但是费尔曼呢，他对打猎没兴趣，他的兴趣就是算数学，而且他不只是算数学，他还有一些朋友，那些朋友也是贵族，都在算数学。费马是这个样子，然后他们常常去用信件来往。费尔曼他有一天他会说，我发现了一个神奇的定理，这个性质，然后他发现一种很神奇的方法可以证明出来。那他的日记都是写这些东西，可是他就不写过程，所以他的那个日记里面就没有任何的这个过程，只有结果而已。后来这个呢被这个称之为费马最后定理。后来呢被很多数学家去拿来研究，发现怎么证都证不出来啊。然后过了300多年了，一直到了1990年，最后一个叫 Andrew Wiles 这个人才把它证出来了。Andrew Wiles， 应该是这样 ，Andrew Wiles 这个人把它证出来，1990还91哦，300年。那他证出来的用的方法是很复杂的，非常非常高深的理论，代数几何什么这些东西的。以费马那个年代300年前是根本不可能的，所以说我们大家一直觉得他那个理论是不是他的证明应该是错的，很多人是这种想法，但是也不晓得。他说突然得到一个，他的日志里面讲说他突然得到一个很简单的、很神奇的证明方法，竟然可以证明这个东西。我们大家认为他那个方法是错的，但是你也不知道啊，说不定就有这么神奇的方法啊，你就没有发现而已啊，对啊，有的时候就会这样子啊，像我也在念书的时候，那时候我在这个明尼苏达大学嘛，那时候我在那边念博士班，就有一个数学系的学长，他的博士论文只有20页而已，博士论文就20页，因为他的博士论文只有20页，那我们的博士论文都200-300页啦，他才20页，为什么呢？因为他就是找到了一个，他突然解了一题 他解了一个 open problem， 然后没有人发现，然后他的指导教授，他们系上教授全部都很 surprise， 所以20页博士论文一样嘛，你想到就想到，想不到想不到。那这个因数分解这个问题，每年都有成千上万的数学家在那边想，到目前为止还是没有什么办法。光是分类它，到底这个问题是不是 NP hard， 都在2003年才有突破。2003年就是10几年前才有。我之前连它是 P 都不知道，就所谓的 polynomial time solvable， 连那个都不知道哦。所以这个问题其实相当难的。好，我们来看一下basic number theory. So, we'll be covering some number theory. 不好意思，有点想打喷嚏，算了，打不出来。Okay. Oh. So the first one is, we want to introduce a special function called Euler-Tauschent function. Now this is a made-up word, Tauschent. This word was created by Leonhard Euler, which is a German mathematician. It's pronounced Euler instead of Euler because it's German. And then this word is derived from Latin. 然后这个Tauschent这个字是一个拉丁文造出来的，就是大概意思就是这么多的意思吧。然后他定了一个函数，然后他不知道怎么取名，反正他就这么多，就这么多，大概是差不多类似这个意思。Anyway, it's a special function. It's an important function in number theory. Let's take a look at this. It's defined as this. You're given a number n. Okay. We find the number less than or equal to n, and then which is relatively prime with n. We count how many elements are there. Let's take a look. So let's find this. Think about this. V6. Now V6, we go over 1 to 6, and then count how many how many numbers are relatively prime with 6？ 小于6，然后呢，小于6的数总共1、2、3、4、5嘛，小于等于6了哈，1、2、3、4、5，然后呢，跟6互质的，因为发现只有1跟5不互质。那实际上我们发现你不需要等于啊，小于等于6，因为你小于6跟6自己跟自己不会互质嘛，所以其实只要看小于它就好。So let's look at another example. This is more non-trivial. Piece 12 this is a good example. So phi 12, we look at these numbers from 1 to 11. Okay. So in this case, we really don't need to consider n because n won't be relatively prime with itself. Okay. So let's look at these numbers. It's enough to consider these numbers up to 11. Okay. Now let's take a look. We're going to delete those who are not relatively prime with 12. So 12 has a power of 12 has a factor of 2. Okay. So we delete all multiples of 2. Okay. So 2, 4, 6, 8, 10. So they're gone. And then 2 and 12 also has a factor of 3. Okay? So we delete all multiples of 3. So 3 is gone. Okay? 6, 9, they're gone. And 12 does not have any other multiples. And any other factors. So what are remaining? What remains? 1, 5, 7, 11. So only have these 4 numbers. That is why phi 12 is equal to 4. So only 4 numbers. This is called the Euler quotient function. And this function plays an important role in RSA. This definition is a little difficult to memorize, so just make sure that you know what's going on, okay? Because it's not very intuitive, okay? So make sure that you just give you any number, you know how to calculate this, okay? The basic definition is, so you guys do an example, you know what it is. If the number is prime, then it's easy. For example, phi 5. 5 is prime. So 5 is prime, then anything smaller than 5 must be relatively prime with 5. So then it's equal to 5 minus 1. So everything. So you only have one less number, which is 5. So if it's prime, then it's easy. Phi 5 is 4. Phi 3 is 2. Phi 2 is 1. These are prime numbers. So they're easy. And if they're not primes, that will be a little harder. So far, the only way to do that is you simply list these numbers and then delete those who are not relatively prime with n. Okay, so this is called Euler quotient function. Okay. There's some properties. We won't prove this, but these properties are important. So the first property is just for reference, for you guys to, it's for reference only. Let's take a look at number 2. Property 2 is the one we'll be using. So if you have 2 numbers m and n, if they're relatively prime, then we have this property: phi n times n is equal to phi m times phi n. 就互质的话可以拆开把这个做。So we have an easy corollary. Now this corollary is what we'll be using. Phi pq. So if pq are both prime, then they're multiple. Okay, pq. We take the Euler quotient function. Because pq are primes, and p is not equal to q. So 2 primes, they're not equal to each other, must be relatively prime. So the phi pq will be equal to, obviously, phi pq, this will be equal to phi p times pq. Okay? And then Cp will be equal to P minus 1, for the reason we introduced. Everything smaller than P must be relatively prime with P. So you're excluding itself. So the total number is P minus 1. And so does Q, okay? So these are the properties I will be using. Another important property. This is the group that Euler found. Okay, this is the. So Euler, think about Zn star. That actually means the. So this is a special. This is a group. This group is quite useful. It actually forms the core of Euler's theorem in this case. So this is Zn star. So what is Zn star? That means we consider multiplication, number one. Okay. So it's a multiplicative group. And the elements are 1, 2, okay, m minus 1, okay, such that they're relatively prime with n. Okay. So this is, you can write it this way. How about this? So this group is consists of number of the numbers, the natural numbers between 0 and n, which are relatively prime with n. For example, Z12. The set of elements of Z12 star is 1, 5, 7, 11. Which we've just shown. So Z12 only has 4 elements, 1, 5, 7, and 11. They are all relatively prime with 12. Okay. So this is Zn12. So Zn star is this. So the number, numbers between 1 and n, such that they're relatively prime with 12. And Euler found that for any positive element, positive integer, this Zn star forms a group under multiplication. And actually, it's easy to understand because we have the multiplication, right? For group, we need to verify four things, okay? Closure, associativity, identity, and inverse. In which the only problem is closure and inverse. Usually these two, because associativity is trivial, okay? Because natural numbers are associative under multiplication, so that should be trivial. But for inverse, it's not, okay? It's not obvious. And then now, if you guys recall that when we talk about AES, we talk about extended Euclidean algorithm. And when we talk about those numbers, mod something, whether or not the inverse exists depends on whether or not that number is relatively prime with n. So in this case, we're excluding everything that is not relatively prime with n, which means for anything that remains, they must have a multiplicative inverse. So we're excluding those who don't have inverse. So that's the idea. And the Euler's theorem is this. It's a little difficult to memorize because these definitions are not very straightforward. So we have, if you take any elements in this group. In this case, we only have 4 elements. You take any element of this group. What we do is we calculate the power, alpha to the power of something, and that number mod n must be must be relatively prime with 1. So it's not very easy to memorize this. So let me give you guys an example. So you take anything, okay? Take anything. We won't take this because this is trivial. If you look at this, we take this, right? This is in alpha 12, right? And then phi n is phi 12, right? It's congruent to 1 mod 12. So that's the first example. This is trivial because 1 raised to the power of anything must be 1. So it's definitely relative prime. It's congruent to 1, right? So this is it holds, but it's trivial. Okay. For the non-trivial ones, for example, you take 5. Phi 12 is 4, right? You know that phi 12 is 4. So this is really non-trivial. 5 raised to the power of 4 is congruent to 1 mod 12. This is Euler's field. 这个就不太 trivial 了哈。我举个例子嘛，大家知道这在干嘛就好。可以简单算一下。Let's do some simple calculation. 好，我算5的4次方，我来看一下。So let's calculate this. 5 to the power of 4 mod 12. Okay. So what we do here is it's a little difficult to calculate 5 to the power of 4. 其实可以嘛，25乘25 625好了。Yeah, let's just calculate directly. So it's how about this, right? Mod 12. 直接算好了，5的4次方嘛，25乘25，你就除看看是不是余4。好，我来看一下，好 ，let's do a little calculation. 好吧 we do this, right? Sorry, 5. So this is 5, and then 25, right? And then 2, 24. But the remainder is really 1. 所以625除以12余数真的等于，这就是 Euler 定。这是 Euler 定。虽然很短，但是有点不太好记。第一个，你的 phi n 的定义有点不是很直观，对不对？这个不是很好记的。建议同学们呢，你就简单算算看，简单做做看。这个 Euler 定理呢，是说你这个 group 里面随便拿任何一个数，这样子都会成立哦。所以你不只是5而已哦，你拿7也会对哦。所以实际上，这个定理告诉我们7的4次方也要同于1哦，mod 的12，11的4次方也同于1mod 的12。啊，那这个是以12为例，所以这定理其实还蛮强的。那这是只是以12为例，你按任意数字带进去，它这个都要对的，知道这个意思。So that's the idea, and then this really makes a huge I should say with calculators. How about this? Let me introduce idea. So this VM, this relationship give us a way to construct this number 1, which is the multiplicative identity. So in other words, if we just pick any elements, we call this element A, and the element is called alpha. So let's see, we start from the element 1, okay, and then we multiply alpha, okay, and then we multiply alpha squared, alpha cubed, so on and so forth. What we know that is up to phi n, it will go back to 1 because this is let's say this is alpha phi n minus 1, and then the next one is alpha phi n. Alpha phi n will go back to the identity. So it's kind of like a clockwise clock arithmetic. Okay, that means you just consider the powers of alpha. It's kind of like going somewhere. Eventually, you'll go back to the origin. So this actually establishes a really non-trivial relationship. You can go some route and then at some point you will go back to the origin. So this really forms the foundation of asymmetric cryptography. So asymmetric cryptography is, let's say you have a plain text, and then you go some route, you end up with a ciphertext, right? But the thing is, this depends on your public key, right? Public key. Well, but instead of reversing every step, which is the concept of symmetric cryptography, for asymmetric cryptography, it actually means you have another alternative route to go back from the ciphertext to the plaintext. That's a huge difference, because you really have to have some deep mathematical properties to facilitate. So you go somewhere, you go from the starting point to your destination through one route, but when you come back, you go through another route. So this actually provides you a way. Just think about this. In the middle, let's say this is your plaintext, and then from this plaintext, you go some route. Okay, if you regard this path as encryption, right? And this is your ciphertext, right? There is an alternative way to come back because of the Euler's theorem. So this really forms the basis, forms the core of asymmetric cryptography. You really have to have some relationship to make this happen. 所以这大概我们可以去理解，就是这个样子。等一下我们就看这个怎么用。所以这个定理其实是非常核心的。等于说你从加密到你从明文到密文，是走一条路，但是回来走另外一条路，你必须要有一种数学的关系。那我们这个关系，这个就是 RSA 的核心，就有这个关系。它告诉我们怎么样走一圈可以绕回来。RSA 大部分就是把这个性质用上去。这个性质在数论里面只是一个非常粗浅的性质。这性质其实大概花个几个小时就可以很清楚的理解它到底在干什么。即便你完全没学过数论也没关系。但是呢 ，RSA 它最厉害的一点就是它把一个这个大家也认为数论是没有用的，数论是真的没用。但是呢，RSA 竟然发现数论有这么一点点用。这数论这个东西基本上都在探讨整数这些相关的东西，这就是数论。数论不太会去，就是说它的重点都是整数的这些关系的，大家去做一些运算。那我们知道，你整数这些东西能讨论的东西已经很少了，对不对？所以大部分都会讨论 mod 这些东西，绝大部分。因为你能讨论的问题本身很有限，谁跟谁骂的几？比方说像费马最后定理啊、方程式啊，对不对 ？x(n 加 y 的 n 次方等于 b n 次方，就讨论一些整数解啊，这大概是这一类这种方程式的整数解啦，或者那我会发现整数这种东西你讨论这些任何关于整数性质可能的要么很简单，要么非常难。整数就是有这种很神奇的性质。所以整数的东西，你不要看它很简单看起来很简单很多东西它只是叙述简单，实际上它的证明可能就是很难。那这数论这个东西，长久以来数学家一直都认为是没有用的东西。那有名的数学家，就一个很有名的数学家高斯，他讲一句话他说数论呢就是数学里面的这个像是一个钻石一样，就是说呢。最厉害的数学家应该要去搞数论，然后呢，去研究数论的这些数学家们，是可以完全的不要管任何其他的东西就是完全为了做数学的乐趣要做数论的。所以数论从以前到现在几乎都没有用。这个是一个很罕见的可以把数论拿来应用的，其实它应用的东西也就是非常粗浅的。这真的是一个应用到数论的东西。其他来讲，数论东西都是讨论一些什么谁跟谁互质啦，谁跟谁骂的几等于几啊这些东西那很多时候你随便写一个东西，那些性质你可能看起来都对，然后看起来很简单，但是它却超难 不知道有没有听过有一个叫哥德巴赫猜想，我给大家讲我的 Gold Box Conjecture。这哥德巴赫猜想呢，就是说呢，比方说我们看这些偶数哈，这个4啊、6啦、8啦、10啊，它是说这个偶数哈，这是一个偶数，2我们先不看，这个偶数呢4呢，我们可以把它拆成什么呢？哈，2加2，那这两个都是质数啊，比方说6等于3加3好了，对不对？8等于3加5之类的啊，那10等于3加7，这两个都是质数。那就有说，哎，是不是大于等于4以上所有的所有的这些整数哈，比方说这大于等于它所有的，比方说2n哈，对不对？是不是都可以写成 p 加 q 呢？这叫哥德巴赫猜想。这个东西到现在是300多年了，还是没有办法做出来。300多年，那你看起来好像很简单了哈。这个叙述太简单了，我们介绍给小学生都可以懂。因为你只需要知道什么叫质数，什么叫偶数就够了，什么叫加，那小学可能就3年级、4年级就可以。你可以跟小学生介绍是叫哥德巴赫猜想，叫 Gold Box Conjecture， 对吧？哥德巴赫猜想，为什么叫猜想呢？因为还没被证明出来。Conjecture， 这个东西难道到现在300多年过去了？还是没有人能够猜，还是没有证明出来。那如果证明出来这个东西对人类有没有什么贡献呢？并没有什么贡献。就像我们要费马最后定理这个东西哈 ，xn 次方加 y 次方等于 z n 次方，只有0.0的整数。这东西300多年来，现在被解决出来了嘛？1990还91嘛，哈，解出来了。这个东西已经解出来，对人类有没有什么贡献呢？我跟各位讲，这个贡献在哪里？其实很有贡献。这个问题已经存在300年，然后大家都一直没有办法解出来嘛。后来呢，曾经被奥匈帝国的皇帝直接悬赏，谁能证出来就给你多少奖金这样悬赏，然后就因为悬赏的关系，哇，这个问题就成为当时最难的一个数学问题。就因为这样子，就大家跑去研究数学。让数学越来越发展，就发展出来成为别的东西，它变成别的数学是有用的。所以因为大家为了要解决这个问题，就去发展数论啊、代数啊这些东西的。然后呢，虽然这个问题本身对人类没有贡献，可是因为大家为了解决它，刺激了大家的兴趣，去发展数学这个东西，造成数学蓬勃的发展，这是它的贡献。哥德巴赫猜想是一样，到现在还是没办法做出来，对吧？而且你知道这个问题难到什么程度哈？这个问题哈，已经有人开始怀疑它是不是不可证的，它真的是证明不出来。你一个这么简单的叙述，数论东西都这样，很多叙述都很简单。那我们知道数学家哈，如果我们看看对数学家做这种研究，其实风险很高。为什么？你看嘛，比方说。假设我们以通讯来讲，好像我是通讯嘛，就工程的东西都不会太难啊，就是基本上就是你做基本上都做得出来，只是说做得好跟做得不好而已嘛，再怎么样都做得出来嘛，对不对？然后应用性也比较高啊。可是数学不一样啊，你如果碰到一个这么难的题目，你一辈子投下去，你可能什么都没有啊，什么都没有。像我们知道有一个很有名的数学家叫做华罗庚哈，大家有没有听过这个？这是一个中国大陆的数学家，毛泽东时代的，是毛泽东很尊敬的一个中国大陆的数学家。这个人一辈子只研究这一题，那就很可怜，因为他选错题目。就他一辈子有什么成就呢？0，没有，因为这一题就是这么短，300年来都没有做出来。那他的不只是他自己一辈子研究这一题而已，他这个人有那种中国人中国人这种不畏苦不畏难的这种倔强的性格，他带了10几个 PhD 也在研究这一题，也就这一题而已。你自己一辈子投下去就算了，你带一大堆博士班学生，像我不会带我博士生去研究这种题， 你自己砸了你1倍就算了，你还全部把你整个实验室的这些学生全部通通赔进去，花不敢买，对。所以呢，你看这个风险是不是很高？一辈子啥也没有。我再举另外一个数学家哈，叫广中平佑，一个日本人，然后一看就知道，这个叫广中平佑。这个人他也是一辈子只做一题而已，他是数学家，对吧？不过他选题目选的比较好，他把那题算出来了，就得了菲尔兹奖。所以这样，数学的研究就这样，你要嘛呢你就得菲尔兹奖，要么就一辈子。这是风险很高，相当于你买股票，你把所有的钱砸下去，好，所有钱砸下去买台积电好了，结果最近俄乌战争一打，然后开始跌，那就赔惨。好，我们先休息一下。Okay, so we continue the introduction. So the Euler's theorem provides us the most important building block for the RSA. Okay, so some examples. So Z15. So Z15. If we, it's customary to use the notation Z15 star if we consider multiplication. If we consider addition, then we can we don't have to delete any elements that are not relatively prime with n, which is 15 in this case. So this is Z15. Okay, we can still have 0. The Z15 star with the star. We delete everything that's not relatively prime with 15. So we have 1, 2, 4, 7, these numbers. So altogether there are 8 numbers. So 8 numbers. According to the Euler's theorem, we have any element from the set. If you raise to the power of 8, it's going to be congruent to 1 mod 15. So this is the example. Z12, we've just seen that. Z12 in this case. Okay, so that's an example. Okay. Now we can introduce RSA. So it's designed by these three professors at MIT. So Ron Rivest, Shamir, and Adelman. These three. So basically, it's based on exponentiation in finite field. In finite group, Z n star. Okay, mod n. Let's take a look. It's actually surprisingly easy. Surprisingly, because they found a really smart application of number theory. The number theory they use is just primitive. It's basic number theory. So first, we find two large numbers PQ. They have to be primes. Okay. So that is why we need to generate large primes. And we'll have a special lecture on how to generate large primes. It's called a primality test. Actually, we cannot generate large primes directly. Instead, we generate large numbers, and then we test whether or not they're primes. Okay, so the idea is testing primes instead of generating primes, because there's no way that you can generate a large prime directly. And if the number is really large, it's difficult to know whether or not they're primes. Okay, it's really non-trivial. So we have a separate lecture for generating large primes later. Okay, it's called primality test. So first we select two large primes PQ, and then we compute the product. No big deal, just multiplying them. Okay, and then in this case, because P and Q are prime, so this phi n is equal to P minus 1 times Q minus 1 according to the corollary we just introduced. Okay. Now, the idea is we select a random number E, which will be the public key. So just pick any element E. And then we calculate its multiplicative inverse, D, okay, of E, mod phi n, mod phi n. So what we want to do is we want this to hold. So E times D is congruent to 1 mod phi n. Okay? So this can be calculated using multiplicative inverse. Right? We're finding the multiplicative inverse of E mod phi n. So if you know phi n, then this can be calculated very easily using extended Euclidean algorithm we just introduced. But this is a really important building block, right? Extended Euclidean algorithm. This will be used extensively throughout this course. So it's not just used in AES. It's used in RSA. It's also used in many other algorithms we're going to introduce. So this can be calculated using extended Euclidean algorithm. So the thing is, if you know phi n, you can calculate this easily. Okay? But if you don't know phi n, in this case, if you don't know P and Q, okay, with the knowledge of P times Q, it's not enough to calculate phi n. So for adversary, it's difficult to calculate phi n with the knowledge of n, okay, because you don't know how to factorize it. Okay, here, if you know how to factorize it, then you can calculate easily. So that's why it's asymmetric. Okay. Now, the public key is E. Okay, and n is regarded as part of the public key as well because everybody knows n. Okay. The private key is P and Q, and also D. Actually, if you know P and Q, it's easy to calculate D. So for a party in the RSA crypto system, you randomly pick E and then you calculate D, okay, according to your private key, and then you're the only person that knows P and Q. Nobody knows D. Nobody knows P and Q, because you're the only person who does this calculation. Okay, so that's the idea. Encryption and decryption. Let's see how to encrypt. The encrypted is the plain text is M. The plain text you first you have to convert it into a number. Okay. In this case, this can be decimal, any decimal number. Yeah. Okay. Because we are everything is calculated mod n. Okay, so your number, your message is just can be any number from 1 to n minus 1. So this is your message n. And then encryption, you simply calculate this power of n. Okay, n raised to the power of e. For some reason, it's just low. No? Okay, great. The encryption is surprisingly easy. You simply raise m to the power of e mod n. That's it. It's done. Decryption, you raise the ciphertext to the power of d mod n. They are these what we're doing is called modular exponentiation. We have a special name for that. Modular means mod something, okay? Exponentiation. That's the critical subroutine of RSA for both encryption and decryption. Modular exponentiation. That means you simply calculate the power of something mod something. It's modular exponentiation. Okay. So surprisingly, it's very easy, right? And why is it true? Because of the Euler's theorem. So Euler's theorem guarantees that if you have a plaintext M, you raise to the power of E, you get a ciphertext. And then you raise to the power of D again, you'll go back to the plaintext. That's because of the Euler's theorem. Let's take a look at why it works. By Euler's theorem, we know that it's for any alpha. So in any alpha, this alpha is a plaintext. You can regard it as a plaintext. You know the relationship of you know the relationship of this. You just keep calculating its power. Okay, Euler's theorem gives you a relationship of how many times you to what extent will it come back to zero? To come back to 1 raised to the power of 0, which is 1. So that's the idea. To what extent will you go back to the origin? So this gives you a relation. So this actually, this makes the encryption possible because it gives you property that, to what extent it will go back to 0. When you go back to the 0, you can convert it back to the plaintext. That, from a purely engineering point of view, if we just understand this from conceptual idea, it's easy. 所以这个其实我们先不要管它证明，先想想看它到底是怎么回事。就是说，这个 Euler's theorem 就告诉我们，你一直考虑它的次方。它到底到了什么程度，它会回到原点？原点就是一的意思，一就是你把它当成一的零次方这样的意思。好，所以这个 M 是任何的一个东西 ，plaintext， 因为它有一个关系，那个关系呢，你会让它回到了原点。所谓回到原点，就是你加密跟解密抵消掉了，最后剩下来的就是剩下 M， 就回到你的原点。所以你加密解密怎么样会抵消掉呢？跟你的 Euler's theorem 有关系。Euler's theorem 就是告诉你，你只要按照这个 Euler's theorem 去取你的这个 public key 跟 private key， 然后呢，你做了一次加密跟解密，它中间的步骤就会刚好就消掉，刚好绕了一圈回到了原点，你就解密解回来。其实就这个意思，啊，大致上是这种想法。那证明其实也蛮简单的哈，但是这个证明我们也是概念性的简单讲一下就好了哈。其实这个证明也并不很那个，其实也并不非常的严格的，但是给大家一个概念性的。好，我们先看一下，所以说关键一步就是在于呢，E 跟 D 呢哈本身的关系，就是呢你 E 再乘以 D 刚好会造成抵消的情形。什么叫抵消情形？就一跟 D 呢，合在一起会造成呢，你一乘以 D 它同于一mod phi n， 同于一mod phi n 的意思就是造成它在次方上面抵消掉，其实就是这个概念。So if we choose E and D smartly such that the public key and private key somehow cancel each other, so eventually you'll come back to your plaintext because you're doing a lot of powers, but most of the powers they cancel each other if you do plaintext and if you do encryption and decryption at the same. If you do encryption and decryption, the result will be equivalent to lots of canceling, and then you go back to the origin. So the key idea is E and D. They're multiplicative inverse of each other, mod phi n. So mod phi n works on the index level. This is the index level. Okay. So for anything that's a multiplicative inverse, mod phi n, if you multiply them, okay, you will end up with this relationship. one times some copies of Vn 啊，就是因为如果说它是两个是乘法反元素的话，mod 的 Vn 你乘在一起呢，你乘在一起就会等于 Vn 的某一倍数，在最后你会剩下一个余数，就基本上是这个意思。那你某一倍数，这些倍数刚好都是绕一整圈，因为你这些倍数就是 Vn 嘛，一个 Vn 就是绕一整圈，等于没有。那你不管绕几个整圈，反正最终你绕下去，这些整圈全部通通都等于，你只要绕一圈就等于完全没动。因为我们这个加密就一直就像是这个时钟在那边绕圈圈一样，你只要绕满一圈等于没动嘛，对不对？所以你到底加密到底会跑到哪里，就是看你的余数嘛。你余数到哪里，就是看你整圈之后剩下来跑到第几个位置。So if they're multiplicative inverse of each other, then this is what you get. The only thing that works is a remainder. Anything that's not a remainder, anything that's a multiple of Vn will have no effect because Vn has no effect because of Euler's theorem. Anything raised to the power of Vn equals to the identity, multiplicative identity. So it will be no use. The only thing that matters is the remainder. Okay, so if we choose E and D such that they're multiplicative or inverse, they will have a reversing effect, okay, the canceling effect. Finally, you end up with multiplying the identity. So you get back to the plain text. That's why RSA works. Okay. So this is kind of like a conceptual idea, but this is not 100%. The main reason is the Euler's theorem is not enough. 这个看起来很漂亮，但是其实还不够，差了一点点。原因在于 Euler 的定理告诉你，你的阿尔法必须要跟这个 n 互值才行。问题就是说，你怎么知道你的 plain text 会不会跟 n 互值？你不知道。对啊，你的 n 是质数吗 ？n 不是质数 ，n 是 p 乘 q， 所以你有没有可能你的 plain text 跟 n 互值呢？有可能。那万一你的 plain 刚好你选的那个 plain text 跟 n 互值，这个就不对了，大概这个意思。后面我会讲到说，即便它不对，它其实还是可以，就是因为我们可以把它推广。So this is what this is for your reference only. So if your plain text is not relatively prime with your n, it actually still works. But the proof on this page will not work. It actually fails when your plain text is not relatively prime. So the problem is, can you find a mechanism to change your plain text somehow that it's always relatively prime to n? Actually, no, because you have no control over the plain text. Just think about that. Who is doing the encryption? Is the legitimate user or anybody? It's actually anybody, right? So anybody. So just let's say one person wants to do encryption. Does he or she know whether or not her plain text is relatively prime to n? No, because that person has no knowledge of P or Q. Because knowing P and Q is the same as knowing the private key. So it has no knowledge. If you have no knowledge of P and Q, how can you be sure that your result is not relatively prime? So you're not sure. So this doesn't work. It doesn't work in this case. Okay, so this proof does not work when the plain text m is not relatively prime. So this proof only works when alpha and n are relatively prime. Okay. So if alpha and n are not relatively prime, we have a proof. It still works, but the previous proof doesn't hold. It's a corollary of Euler's theorem. So yeah, this is for your reference. Okay. even though it does not hold, we can have this relation. Okay. So this is for your reference only 哈。那这个部分就给大家当参考。那如果它不，你既然没有办法控制你的明文是跟 n 互指的话，好，刚刚的证明就不对了。不对呢，虽然刚刚的证明不对，但是 RSA 还是对的。所以 RSA 可以告诉我们说，其实真正的标准的 RSA 证明不是用刚刚那个 Euler 定理的，它其实它比较考虑一般的情形，就稍微复杂一点。但这还是对的哦，还是对的。Okay, so anyway, now let's talk about modular exponentiation because this is the most important building block of RSA. So we're going to talk about modular exponentiation because we're doing a lot of we calculate a lot of exponentiation. I mean the power of something mod something, and this has to be calculated in an efficient way. Okay, so let's take a look at exponentiation, and then we will come back to show an example of RSA. Okay, now let's talk about modular exponentiation. 好，我们来看一下，现在这是一个高同学怎么算，这个怎么算？先教大家用手算的方法，然后呢，写程式的时候有一点点不一样，但这个差异没有像之前这个 extended Euclidean algorithm 差这么多，基本上还是差不多。Let's take a look. So let me show you how to calculate the modular exponentiation of any number. So the idea is, if we randomly write something, really big numbers. Actually, you don't have to write really big numbers, but it's not easy to calculate. So, straightforward calculation is not does not work. If we just write something like this. Okay, if we just write something like this, it's really big. Okay. Well, you have 3-digit number and a 3-digit number. Just think about how large it is. Okay, the 3-digit number. Let's just calculate. Okay, let's just estimate. Okay, it's something like 100. Okay, so it's 10 to the power of 2, right? And then you multiply 400 or something. That's altogether okay, something like this. That's 900 digits. 我只是随便写3位数而已，这样就是多少？900位数，有办法直接算吗？对啊，所以显然这个会有问题的嘛。这个我不特别介绍，算法会有问题。次方你随便写个几位就很大了，才3位就这么大啊。那我们知道 RSA 是几位？600位，至少300位。这个300位，300位数的300位数次方，这样有多大？怎么算？直接算是绝对没办法。最普通的计算机只能算8位数，你就随便一写就900位数就爆掉。所以我们现在跟同学讲这个怎么计算。Okay, so, if you just randomly write something, this has to be calculated in an efficient way. Otherwise, there's no way you can implement RSA, right? Okay, so what we do here is, number one, first the idea is to reduce this number so that it will be smaller after one iteration or something, okay? So first we factorize this. So this 456 can be factorized as 2 times 2 to 8, okay? And then what we can do is we can pull in the factor. The factor of 2. We can regard it as this. Okay, let me omit the mod 789. So this is 122 squared. If that's calculated, so this can be calculated directly. So 120. So this is equal to 15129 raised to the power of 2 to 8. 2 to 8 mod 789. Okay. 好，先这样。那现在是这样子哈， 我们这个15129可以先骂的789，因为其实这些乘法这些东西，它其实你先骂的再乘，或者先乘再骂，其实都可以，本身就这性质。那我们先骂的话，那15129就被骂得掉，那骂得掉789就变成一个3位数的。So this is 15129. Let's do this. Okay. What we do here is we can do this mod inside. Okay. We do this mod inside. Then after that, we'll reduce this 5-digit number to a 3-digit number. So this can be done using easy calculation. So this is actually equal to 138,228 mod 789. Okay, so this is one iteration. You have a number, right? You actually reduce this this index, this power to a smaller number, significantly. So if we repeat this process, then it can work, right? 好，所以这样就变小了，这样除下就变小。好，那么我们来看一下下一步怎么办啊？我先把这步抄过来。So let's take a look at this, and then what can we do next? Okay, so this is one iteration. Let's look at the second iteration. Well, we can still factorize this to 8 because this is equal to 2 times 114, right? Okay. So we can do this as well. Okay. So this is 114. Okay. So this can be something, right? Something, and then how about this? 114 is a 557, 2 times 57. So that is okay. Okay. So this will be something like 57. Now we have a problem. 好啊，你这样子，我是随便乱写的，那就114再分解成2乘57，这都还 OK。哎，57怎么办？好，现在问题来了，57怎么办？那现在这个我这个虽然是乱写，但是很妙的是57还可以提出3出来，所以57可以变成，这正好可以变成3乘以多少？19。好，这都还 OK 哦。好，那就越来越小了嘛，对不对？你3次方还可以算嘛，对不对？好，问题来了，你最后变成19怎么办？这个东西是质数，没办法做下去了，对不对？怎么办呢？有没有同学知道这样怎么办？10到19，这变质数了，质数就没办法分解了。原本你可以越乱写一个很大的数，然后一直分解，越来越小，变成质数。So originally you have just randomly write something, and then you can factorize. And then once you can factorize, you have small factors. Then you can do straightforward calculations, and then reduce the index to an extent that it becomes a prime number. If it's a prime number, there is no way you can keep going, right? So in that case, it won't work. So let me show you how to deal with this case. Okay. If it's a prime number, what should we do? So let's think about this. So if we can solve this problem, if we can deal with this case, then it's okay. The idea is if it's prime, then we do it this way. We pull out a factor of 123, and then this is what we do. So this becomes an even number. So this even number will always have a factor of 2, right? So this becomes, right? So this can be calculated, right? This can be calculated. So this can always be calculated. But once you get the result of the parentheses, you multiply another copy of 123. So that's the idea. Okay. So using this method, then we're not limited to anything that has a small factor. Even if you don't have a small factor, you can pull out the factor itself. So instead of finding smaller factors, then what we can do is we can think about whether or not this index is an even number or an odd number. So we can represent this number as, using binary representation. Let's see, if this is 19, right? So 19 is what? Using binary representation, 19, let's calculate 19. So 19 is 16 times 3, 16 plus 2 plus 1. Okay, so using binary representation, 16 is 2 to the power of 4 plus 2 to the power of 1 plus 1. So this is 19, right? 19. 2 to the power of 4 is this, okay, plus 1, 1. So it's actually this, 1, 0, 0, 1, 1. So this is actually 1, 0, 0, 1, 1, okay? So this gives you information of whether or not it's an odd number or even number. So if we represent this 19 as a binary number, so we use binary representation, right? 1, 0, 0, 1, 1. Then it gives us really good information of how to handle this, right? So this is 1, 1, 0, 0, 1, 1, right? Becomes, using binary representation, that's a lot easier because if we pull out a factor, this is 1, right? Times right? Okay. So this becomes an even number, right? This is even. The even number has, using binary representation, has a 0 at the end, right? So then you can factorize it this way, right? Like this, times. Square, right? This is square. This is actually square, right? This is square. This is square. Then, right? So using this, what we do here is, if the last bit is 1, then we pull out a factor here. And then we do the square, and then we do the right shift. Right? So we'll keep doing that, Eventually, we'll end up with smaller numbers. Okay? So if it's an even number, we do a square and then right shift. If it's an odd number, we take the odd number here, and then square and do a left shift. Okay? So the idea is to represent this. If you represent this power using binary numbers, it's very easy to do that. Then we can end up with this very easy algorithm. Please note that I forgot to mention that this actually calculates a to the b mod n。这边我这一章讲漏写，请同学注记一下这个是什么东西 ？a 乘以 a 的 b 次方 mod n。我会直接补上去。So this is a to the b power of b mod n. Okay, and then this b, we have this bi here. Bi is simply the binary representation of power, okay, of the exponent. So bi, okay, binary representation. Okay. So these C and D, they are just temporary numbers. This D, see, the temporary numbers we use to handle the exponent. Okay, we handle the right shift, that kind of thing. Okay, so and the D is a temporary number. D actually saves the information of how many copies you want to do this multiplication. Okay, and then B is represented as BBI. Okay, so this is actually a very short algorithm. Okay. Implementing this way, modular multiplication, modular exponentiation. Okay. So let's look at one example. 2 to the power of 21 mod 22. This is one example. Okay. So this 21 is represented as 10101. This is B1, B2, B3, B4. Okay. So this implements the method we just introduced. Okay, so this is modular exponentiation. So when you guys implement this, modular multiplication is a very important building block as well. This will also be used in other asymmetric crypto systems too, not just RSA. It can be many others as well. Okay, so this is modular exponentiation. So this gives you an idea. Like 2 to the 21. 21 can be represented as 16 plus 4 plus 1. Okay. And then it implements this calculation. Okay, let's come back and look at an example of RSA. Just look back an example. First, we choose 2 primes to illustrate the RSA algorithms. We use smaller primes. If in practice, these primes are really big, like 300 digits or something, 1024 bits. Current standard is this. So this P and Q, they're both 1024. So N is equal to P times Q, which is about 2048 bits. So it's really big. Using decimal representation, it's 600 digits. Okay, more than 600 digits. It's really big. So P and Q. And then we compute N. N is equal to P times Q. So in this case, it's small. It's 187. Okay? And this phi n. Phi n is P minus 1 times Q minus 1, which is 160. So this is only known by the legitimate user. So this is part of the secret key. Phi n is part of the secret key. Okay? So we select E and calculate D. In practice, we can select E so that E is small, because E is for other people, for anybody to encrypt. So usually you choose a small number, so then it will be efficient, right? Because anybody sends you some encrypted message, the calculation will be fast because the encryption key is small. So E can be really small. In this case, we choose E equal to 7. And then we determine this, right? We calculate its multiplicative inverse. So this can be done using the extended Euclidean algorithm, right? Extended Euclidean algorithm. You guys know what to do that, right? What to do. We already show you guys how to do extended Euclidean algorithm, both for hand calculation and writing program, right? How to write a program to do that, right? So we remember that last time we talked about we introduced 2 sequences, S sequence and T sequence. We can use that, right, to find the inverse. And then this is the public key and private key. The private key is this P and Q, okay? P and Q 17 and 11. These are the private key. Okay. Encryption. Now let's to show that even if the plain text is not relatively prime with n, it still works. So I deliberately chose the secret message to be 88. Okay, this 88 is not relatively prime with 187. 这是我们故意把它选一个那个这个 message 是88，故意选的，就是要给大家一个例子看，就是说，即便是它不是互质的，它其实还是对的，而 RSA 是对的，虽然说你的 Euler 定理是不对的，其实 Euler 定理是帮助我们理解而已。对，我讲 Euler 定理啊，因为我们现在的这个 public key 是187，187是17乘以4，所以你所有跟11跟17，就11跟17的倍数，在它这个都是错的，你 Euler 定理都不对，所以你11、22、33、44这些通通不行，然后17、34这一些 plain text 是不行的，它的 Euler 定理是不成立的。So for these plain texts, multiples of 11, multiples of 17. Euler's theorem would not work because it do not belong to the multiplicative group Z187 star. Okay, so let's choose a plain text which is not relatively prime, just to show you, even though the Euler's theorem cannot work in this case, the RSA is still correct. Okay, so the message is 88. The encryption, 88 raised to the power of 7, okay, because 7 is the public key with mod 187. The result is 11. And the decryption, 11 raised to the power of the private key, which is 23, it still works. Okay? So this also works. Okay? So this clearly shows that the modular explanation, the RSA is correct. Okay. Let's take a look at some remarks. The hardness to invert RSA. Okay. How to crack RSA? How to attack RSA? Okay. What you can do is, okay, let's take a look. How to attack RSA. And how to attack RSA, let's see, how to compromise RSA. So to compromise RSA is that you can decrypt, right? What do you need to decrypt? You only need D, right? If you have D, then you can decrypt, right? The algorithm is here. Let's see here. Right. The decryption, because this N is public, okay, and the ciphertext C is known. You only need D to convert it back, right? So to crack RSA is that given the public key E and N, okay, if you can compute D, then RSA is compromised. Right? So, given E and N, okay, find D. In this case, RSA is compromised. Note that you really don't need P and Q. If you have D, that's enough to compromise RSA, right? If you know P and Q, then definitely you can calculate D because you can calculate the multiplicative inverse. However, without the knowledge of P and Q, is it possible to determine D directly? It could be a little easier, right? The thing is we don't know. And so far, no mathematicians know that. Whether or not this is possible, they don't know. So far, the only way to invert RSA or to crack RSA is to factorize N. So then you get P and Q. Okay. Is it a way to determine D directly without factorization? We don't know. mathematicians don't believe that. So the best way to invert RSA is factorization. And integer factorization becomes a very active research area. There are lots of hundreds of mathematicians, thousands of mathematicians. They're researching on this every year. So every year there are new results. Okay, so far, let's see. There are only some partial results to how to factorize particular numbers. For example, you have some number of a particular format. In some cases, you can factorize, but so far there's no known algorithm that can factorize every possible n. So there's no known algorithm. But do they exist? We don't know. Okay, we don't know. If anyone finds an algorithm that can factorize any number efficiently with a proven, theoretical bound, then the whole RSA system will be useless. It's completely done. So in short, it's like that. 所以说现在这个因数分解会是一个还算蛮 active， 每年都有新的一些结果。什么样的？有些他们没有办法去分解所有可能的 n 啊，都是你有特定形态，比方说它这个还是4倍的某个数再加什么东西怎样的，这个它可能可以分解，某些情形可以分解。那某些情形分解的话，那这个时候那你 RSA 在这一些 n 你就不能用，因为你可以很快速的被分解，对不对？所以说呢，那现在情形就是这样，就是说每年都有新的结果嘛。好，那你有一些这些 n 呢，你可以很快的被分解。那么我们 RSA 在选取参数的时候，我们就不要去选那些 n， 就是这样子，就不选那些 n， 避开那些 n。那避开那些 n 就像是你就像有一个 patch 一样，就是说你那个程式我多加了几行这个条件，我的 n 不能选这种 n， 这样就好了，然后就一直还是可以用，就这样子用了40几年。45年一直到现在，然后这45年来，始终没有任何一个数学家可以找到一种因数分解的方法。那它是对所有任何的 n， 它都可以很快的分解，目前是没有办法的。但是它没有办法，是不是代表你是一定不行呢？其实还是有差距的，搞不好它可以啊。我的意思是说，你如果可能是因为这些数学家数学不够好啊。所以你找不到啊，你找不到你怎么说它一定不存在呢？这个是差距很大的。但是现在的情形就是这样，就是呢又找不到，然后呢又也没有办法证明它不行，那好像也没太大的问题，大家就继续用吧，情形就这样子。所以现在情形是这样子哦。所以呢，这些演算法都已经公开，都已经是这样子，然后呢看起来好像也 OK， 但是也没有什么办法能够证明它是很完美，其实它也不完美。会不会有可能哪一天有人发明出一个方法，让它可以很快的找出来呢？不知道。如果一有的话 ，RSA 就完蛋了。那你整个所有的这些这个，不管是虾皮啦，或是整个你的这些这个电子商务啊，你那个远距的这些这个 security 这些什么 signature 啊，全部通通都不能用。如果那一天发生的是大家全部改朝换代的时候，这一类演算法完全不能用。不过还好，这个演算法就算 RSA 不能用，还有别的演算法可以用。目前来讲还没有一个方法是说让全部通通毁灭性的这样子那其他的演算法有没有说证明它呢是绝对安全的呢？是不会被破解的呢？我们马上要教到另外一种方法，是 discrete log 的版本。那其他的方法有没有它可以证明说，你确实是一定找不出来呢？也没有。所以我们现在的情形就是说，所有的这些演算法都是用了这40年，好像40多年，好像也没什么太大问题虽然不完美，但是也是大致上还是可以用。这就有点像什么呢？你说这些东西安不安全就像是我们去邮局寄信，会不会到？也是简单这个道理。你说邮局寄信会不会到？有没有办法保证一定到呢？我跟你讲，没有办法保证。现在邮局找一大堆工读生，邮局员工不够，我就寄过东西调过啊。我曾经寄给我一个长辈一个礼物很多年前， 他就是寄掉了啊，对不对？那他也只赔我，他只赔我1000多块啊，我的礼物超过那个价值，那也没办法啊。你就算是报值，他赔你最多的上限也就只能是，好像是5万块以内啊。所以说邮局是不是一定会到呢？它不能够保证的，它还是有风险。但是你大致上你寄个100个，还是有90几件到嘛，是这样子。所以你知道吗？这个东西是有一点风险，但是你并没有一个明显的缺点。所以就是说这种东西有没有用，大概是这种情形。所以大家也不能够太过于相信这些系统，因为到最后都是变成数学问题。这个东西有没有办法被破解？是不是可以证明不能被破解？数学上几乎都是没有办法的。我们在整堂课教的所有的演算法，几乎都没有办法证明说是完美，数学上是不完美的，那就是工程上可以用而已。好，我们今天先讲到这边。